Hello and welcome to this fourth video in a series on nitrogen chemistry aimed at National 5 level. So what have we seen already? You should know that artificial fertilizers generally contain chemicals called nitrates. Nitrates are very important for the growth of plants. Now we can make nitrates by neutralizing nitric acid. That's what nitrates are. They are salts made from nitric acid. The nitric acid can be made using the Haber process. That's what we looked at last time. And that involves reacting ammonia with oxygen. After a couple of steps, that produces nitrogen dioxide, and that dissolves in the water to form nitric acid. The actual process is a little bit more sophisticated than that, as you may recall, but that's all we need for this video. That takes us then to the Haber process. That's what's going to give us the ammonia we need to make the nitric acid. Now, this chap is Fritz Haber. He was responsible for chemical weapons for the Germans in the First World War. That means he's never going to get a reputation as a philanthropist. There are many stories told about Fritz Haber which are not at all pleasant, but some of them certainly are war propaganda. Anyway, in 1909, before all that unpleasantness started, he developed the process to make ammonia. And it's really, in some ways, very, very simple. Ammonia is nitrogen hydride. So we take nitrogen. Where can we get nitrogen? Duh, we get it from the air, by a process called fractional distillation. The other thing we're going to need then is hydrogen. We get this by cracking methane, usually. There are other ways, but this has been the most common way up to now. So, ammonia is nitrogen hydride, NH3. All we've done is put together the elements that are in ammonia. We call this a synthesis reaction. Okay, so what does it involve? Well, let's take a reaction vessel. Now, this is going to have to be very, very strong, because this reaction is carried out at high pressure, about 100 atmospheres. It's going to need a catalyst. Now the catalyst is iron powder. And what we're going to do, we're going to heat that up to a moderate temperature of about 450 degrees Celsius. Notice that's a moderate temperature. It's pretty hot, but not very hot. We're going to look at why in a moment. Okay, let's bring in our reactants, our nitrogen and our hydrogen. The reaction goes ahead and they combine together to make ammonia according to this equation there. I've balanced it up there in the equation. 1 molecule of nitrogen combines with 3 molecules of hydrogen to make 2 molecules of ammonia. Now you might think that's all hunky-dory. That looks straightforward, but the thing is, that reaction there also works backwards. In other words, ammonia breaks up to make nitrogen and hydrogen again. In fact, what's going on in the reaction vessel is a combination of the two. It's a reversible reaction, something we normally call an equilibrium. Now what that means is that in here, you've always got a mixture. You don't just have reactants, you don't just have products, you've always got a mixture of the nitrogen and hydrogen and the ammonia. The only question is how much of each, and that depends on the temperature. At very, very high temperatures, you get lots of that, which is what you don't want. But at very low temperatures, the reaction is too slow, especially if you're talking about pumping gases. So what you want is a moderate temperature, a temperature where you get a reasonable amount of ammonia reasonably quickly. Okay, so what do we do then to get the ammonia? If we've always got a mixture of nitrogen and hydrogen and ammonia, what are we going to do to get the ammonia we want? Okay, let's get our reaction vessel back. There's our nitrogen and hydrogen, and our ammonia mixed together. Remember, you've always got a mixture of them. Right, let's pump that into another reaction vessel. Okay, there we go. There goes the ammonia, the hydrogen, the nitrogen. And what we're going to do, through that weird looking pipe on the right, we're going to pump a coolant. That's a liquid with a temperature below minus 33 degrees Celsius. So what that's going to do, it's going to cool that container, that reaction vessel, down below minus 33 degrees Celsius. Why is that important? Because minus 33 degrees Celsius is the boiling point of ammonia. So if you cool the ammonia down below minus 33, it will condense to form a liquid. And that can just be tapped off. And that's the ammonia. You've now got the ammonia you wanted. What are you going to do then with that nitrogen and hydrogen that seems to be building up in the tank at the top there? Well, we put a wee tube in like that, and we pump the hydrogen and the nitrogen back to where they started. In other words, we recycle them. Okay, so this just brings us to a summary. That chap, by the way, that's Carl Bosch. He was the guy who was responsible for taking Haber's idea and in 1913 producing ammonia industrially for the first time with a company called BASF. So what does the Haber process, or in fact the Haber-Bosch process I suppose we should call it, what does it involve? It involves reacting hydrogen, which we get from natural gas, and nitrogen, which we get from the air. We do it at high pressure, about 100 atmospheres. We do it at moderate temperature, about 450 degrees Celsius, because remember that's a kind of trade-off. It's a temperature that will give us a reasonable amount of ammonia reasonably quickly. And you want an iron catalyst. That's your reaction. There, that's the equation. Notice it's an equilibrium. That means you've always got a mixture of ammonia and also nitrogen and hydrogen during this process. We separate the ammonia off though by cooling it below its boiling point, and then we recycle the nitrogen and hydrogen. Okay, that's it for now. Thanks for watching. Bye just now.